Okay, today I'll be telling you about Gröbner objects in Schubert calculus. First, I will say what Schubert calculus is. So you might sometimes hear complicated adjectives in front of Schubert calculus, such as Affiliation, quantum, affine, K-theoretic. I'm not going to talk about any of those today. I'm going to stick with a very classical setting. So this is Schubert. He could not possibly have been a member of the IAS. But Schubert invented Schubert calculus, which arises from questions in enumerated geometry that concerns with linear spaces. For example, how many lines pass through two given points? And how many points do two lines intersect? Here's maybe a less trivial one. If you haven't seen this, it's fun to think about and see if you can come up with an answer. If you don't know, you're welcome to ask me for the talk. So how many lines in three-dimensional space? Four general lines in how many lines in three-dimensional space pass through four given general lines? That's a question. So the modern formulation of Schubert calculus is through language of algebraic variety. In particular, here's a algebraic variety where it packs a lot of these incidence relations of linear spaces. So for example, here's the central object, which is the complete flag variety in the of the complex n-dimensional space consists of the set of nested chains of vector spaces, such that the ith vector space has to have dimension I. And this complete flag variety can be identified with the general linear group modded out by invertible upper triangular matrices. So if I want to write down a specific flag, I can write down a invertible matrix, and I can take the span of the first I vectors that gives you the ith vector space in my flag. And there is special ones given by these things called coordinate flags. So given a particular permutation, I can take the permutation matrix. I can take the span of the first ith vectors by permutation matrix, and these are going to be coordinate subspaces, and these are special flags called coordinate flags. They're in Sn, they're n factorial of them. And when I want to talk about instance of linear objects, one natural notion is what I would like to consider relative positions of two flags. So here, the notion of relative position is defined as the following. So given two flags, I can measure the relative position between them by computing the pairwise intersection of the vector spaces, dimension of the pairwise intersection of the vector spaces of the two flags. So in this picture, I sort of show you how the relative position with respect to a fixed reference flag can vary. The most special position is that any given flag directly coincides with your fixed reference flag, and then you can slowly move it away from the fixed reference flag in these prescribed ways, and at the top I have the most generic situation. So this gives us a stratification of flag variety by Schubert varieties. So here's the definition of a Schubert cell. So I told you about the coordinate flag and the reference flag. So here I will take the reference flag, the flag given by this longest permutation. So I fix that reference flag. And for any given coordinate flag, this is going to prescribe for me a relative position. And if I want to define a Schubert cell with respect to this given permutation, I will take the set of all flags that have the same relative position with the reference flag as a prescribed relative position. So that's the definition of a Schubert cell. And if I take a closure, that's a Schubert variety. So this will give me a stratification of the flag variety by Schubert varieties. So the natural inclusion induces the order of the permutation, and this is can be taken as a geometric definition of the strong Bruhat order of permutations. Okay, and one significance about Schubert varieties is that the cohomology classes of these Schubert varieties, they form a basis of the cohomology ring of the complete flag variety. This comes from the stratification. So now I have a ring with bases. So there's three basic stages of understanding this cohomology ring of the complete flag variety. The first stage is that we would like to present this ring. So this is answered by Burrell in 53. he says that the cohomology ring of the complete flag variety over the integers can be identified with a quotient of the polynomial ring in variables by the ideal generated by symmetric polynomials without constant terms. So now I have explicit presentation of the cohomology ring as a quotient ring of a polynomial ring, which is very explicit. And the second stage of understanding the cohomology ring is that I would like to find good polynomial representatives for these Schubert classes, because sometimes it's difficult to work with classes. It would be nice if I can work with polynomials. So this is also solved by the Scu and Schussen-Berger in 82, but there's still furious research that studies a structure of Schubert polynomials and related polynomials. And finally, the major open problem in this field is that we would like to give sometimes what's called a combinatorial interpretation of these Schubert structure constants. So I will go into too much detail of the status of the open problem, just that this is the problem that as a community we're collectively stuck on. Only special cases are known. And you might ask me what I mean by computing these structure constants in manifestly positive way mean. So sometimes people say this, we would like to find a combinatorial interpretation. The most rigorous definition I know of this notion comes from computational complexity theory. So, and there are opinions that maybe there are some fundamental obstructions to hoping for such a combinatorial interpretation to exist. But geometrically, this is kind of easy to understand. So our structure constants are always going to be non-negative integers. In the way that I can use intersection theory to express these structure constants as counting points of generic intersections of these Schubert, of a triple of Schubert variety satisfying certain dimension conditions. Okay. And let me come back to Schubert polynomials. So I said that Schubert polynomials are particularly good representatives. In what sense are they good? So they're polynomials that form the basis of the polynomial ring. And they have the feature that when I multiply two Schubert polynomials, they recover these Schubert structure constants. So here I give you the small examples of what these Schubert polynomials can look like. And they're very nice combinatorial formulas for Schubert polynomials. The first one, that's probably also the most famous one due to Berger and Billy, is that in order to compute Schubert polynomials, I can enumerate these combinatorial objects. So these combinatorial objects are called pipe dreams. So for each permutation, I have a particular way of tiling my grid by these specific kinds of tiles. So in this case, I have crosses and elbows. And after I tile my grid, I would like to see these pipes traveling from the north edge to this west edge. And then they would record the way that they intersect will record this permutation. So for every permutation, I can enumerate a set of pipe dreams for this particular permutation. And each pipe dream is going to associate a weight. So if I sum over all the pipe dreams and for each pipe dream take their weight, that recovers me a combinatorial formula for the Schubert polynomial. And relatively recently, Lamley and Shimanogo discovered a different combinatorial formulation of Schubert polynomials using these different combinatorial objects called bumpless pipe dreams. And these, again, there are certain different tiling the grid such that once you tile it, you have these numbers traveling from the bottom edge to the right edge, and then I can associate a weight to each of them. I sum over everything that associates to a given permutation. I recover a formula for my Schubert polynomials. So these are in spirit similar, but actually very different combinatorial objects. And the point here that I would like to stress is that these pipe dreams and bumpless pipe dreams are not just combinatorial, there's geometry behind them. So these are what I call Gröbner objects. So I'll say a word what that means. So the general framework that we do in geometry is very common thing we do in geometry is degeneration. So we have something geometric, we would like to degenerate it so that it becomes geometrically simpler, and but so then we can study this limit. So Gröbner degeneration is one such thing. So the general setup is that I have a variety that I have a torus acting on this ambient affine space. I have a one parameter subgroup, and I can take this t to 0, and I take the limit of this action. So the limit will be for if I take the one parameter subgroup to be generic enough, the limit will break into a union of coordinate subspaces, and this is geometrically very simple, but this is essentially a combinatorial object. And the nice thing about this process is that the limit will carry geometric information, especially the cohomological geometric information about X that you can study through an array of techniques using combinatorics. So the pipe dream is such an example. The ambient, the underlying geometric spaces, that geometric varieties that we get pipe dreams from are called matrix Schubert varieties. So let me say a few words what those are. So given a permutation, I can define the matrix Schubert variety to be the closure inside the matrix space of the pre-image of the Schubert variety given by W. So under this natural quotient. So this is now actually living in the affine space. So I can use a lot of commutative algebra and algebraic computation tools to study these kind of matrix Schubert varieties. And they also are closely related to the Schubert varieties in the complete bag variety. So for these matrix Schubert varieties, I can explicitly write down the generators for these ideals. These are called Fulton generators. A feature of these generators is that they're all determinantal. So you can write down the equations as minors of some matrix. So here's an example for W equals 2, 1, 4, 3. And pipe dreams arise as a limit of a particular kind of Gröbner degeneration. So here, anti-diagonal degeneration here is just some specific degeneration order that I take, such that when I take the matrix Schubert variety, take their limit, and the limit is going to be break into components, and each component is going to be indexed by a pipe dream. So the pipe dream can recover this. Can record what happens in the limit of degenerating the matrix Schubert varieties. So similarly, bumpless pipe dreams can be interpreted as coming from a different type of degeneration of matrix Schubert variety. So here, the terminology is the diagonal degeneration, and this is work done by Patricia Klein and Anna Weigand. Patricia Klein is here. Okay, so in my work with Ivo Gal, we show that there is a canonical bijection between between pipe dreams and bumpless pipe dreams. So this bijection is completely combinatorial. Canonical in the sense of combinatorics, but we don't know whether there is a nice Gröbner geometric interpretation of such bijection. So that's a question. So one other reason I care about these objects is that they have combinatorial applications. So I mentioned Schubert calculus seeks to find combinatorial interpretations of the structured constants. So these pipe dreams, and in particular bumpless pipe dreams, can be used as a sort of combinatorial abacus for Schubert calculus. So I'll give you a proof of concept. So here I show you a basic formula of Schubert polynomial. This is just the expression in terms of polynomials. But with bumpless pipe dreams, I can invent these algorithms, combinatorial algorithms that basically operates on these bumpless pipe dreams and realizes my identity on the level of Schubert polynomial. So you can sort of see that by designing these algorithms that I can express these identities come from polynomials, I can sort of use them as an abacus. So this is only, where's my, only a proof of concept. So using this kind of techniques, me and my mentor in Minnesota, Kwiatkowski, we did several positive combinatorial rules for some special cases of Schubert structure constants. Okay, so finally, in joint work with Matt, who is here, we studied the, we would like to have some sort of understanding of the all Gröbner degeneration of matrix Schubert varieties. So this is we're saying that we're not particularly biasing for or against any sort of degeneration order. So can we say something in general? So we study the closure of matrix Schubert variety in a product of P1. So we projectively complete each matrix coordinate. And we define Schubert polynomials to be the multi-degree of this closure. This somehow controls, in a sense, all possible Gröbner degeneration of the matrix Schubert variety. This should be a bar here in matrix Schubert variety. And one application of this perspective is that when my permutation satisfies some special condition, here we ask for the Schubert polynomial and the Schubert polynomial for the inverse permutation to be multiplicity free. We were able to give an inductive formula for these fine Schubert polynomials and also give a universal Gröbner basis for the matrix Schubert variety in these particular special cases. And I will end my talk here. Thank you very much.
Any questions to Daoji? Is there analog for reductive groups?
Analogs of what?
Like all this thing. So as far as I understand it, this is for GLN, right?
Right. Oh yeah. So there are other. Right. So I guess so Schubert decomposition of course makes sense, right? So it works for general flag varieties. So in type A we have specifically nice Schubert polynomials. So I think in type C we have something which I'm not particularly an expert of. We have something in type C. We definitely don't have it for every type, and we definitely don't have a type independent way to come up with these polynomials.
So not yet, or you don't see?
I think there are some obstructions, but I don't understand. Yeah, I think maybe there are people in the audience.
So for classical type.
Yes, classical types we have, Lyman polynomials.
What about G2?
So G2 you can come up, but these polynomials have special properties, and if you want all those properties for exceptional types, you can write, but they will not have good properties.
Also, are there stories on the affine Rachmaninoff?
There are. So you can sort of play the same game. So there's an analog of these kind of the matrix Schubert story, which is in somebody's thesis. It's not published, so you can do it for affine Grassmannian. And I have work on the affine flag variety that tells you how to compute equations for the Cauchy-Lustig varieties and give a Gröbner basis. So I know how to generalize this matrix Schubert story to like a infinite by infinite matrix.
One last question for no questions. Let me just take this.